Section 7.3 is on estimating a population standard deviation, or variance. And in order for us to do this, we need to use a different type of distribution here, a chi-square distribution. So it's denoted by a Greek symbol, kind of looks like an X, but that's really chi. And the distribution itself is chi-squared. In a normally distributed population with variance sigma squared, if we randomly select independent samples of size n and compute the sample variance s squared for each sample, then the sample statistic chi-squared is equal to n minus 1 times sample standard deviation s squared divided by population standard deviation sigma squared. Well, I should actually probably say these are not standard deviations. The chi-squared test statistic is n minus 1 times the sample variance divided by the population variance. As a chi-squared distribution, we denote a right-tailed critical value by chi-squared sub r and a left-tailed critical value by chi-squared sub l. We need to use both for this confidence interval. Have to. We use the degrees of freedom of n minus 1. And SAS could find these as well if we wanted to code it to do so. Or we could use table A4 in the textbook. The only problem with that, though, is that, you have issues with rounding and whatnot that may or may not cause an impact. But for the most part, we would be using SAS to find these calculations. So a chi-squared distribution, this first picture up here, it's skewed right? We have a whole bunch of data here on the left, and it skews off to the right. It is nowhere near symmetric. All values are non-negative. It goes from 0 and higher. And it's definitely not like the normal or student t distributions, as you could tell. It can be 0 or positive, but not negative, so it's non-negative. It's different for each number of degrees of freedom. As the degrees of freedom increases, the chi-square distribution approaches a normal distribution. As you can see with the degree of freedom of this first one here is 10, right? It's still skewed right, heavily. The degree of freedom of 20, notice how it's still skewed right? But it's closer to a standard normal distribution. And the higher the degree of freedom, that much more it becomes more like a standard normal distribution. So, for example, a simple random sample of 22 IQ scores is obtained. Construction of a confidence interval for the population standard deviation sigma requires the left and right critical values of chi-squared, corresponding to a confidence level of 95%, and a sample size of 22. Find the left chi-squared value for the critical value of an area of 0.025, and the right and the left tail and find the chi-squared value to the right for the critical value of an area of 0.025 in the right tail. This uses a degree of freedom of 21. Since the sample size was 22. And inside of SAS, we can find the chi-squared value to the left to be 10.283, using that 95% confidence level and whatnot. The chi-squared value to the right is going to be 35.479. Alright, so inside the textbook, it uses that degree of freedom of 21 and a cumulative, this is right distribution of 0.975 and 0.025 for the left and right, respectively. And inside of SAS, it's very similar to that. Let's look at the video for the chi-squared confidence interval. But we would have those two, and that is what we would use for the confidence, for the, well, a part of the calculation for the confidence interval. The confidence interval for estimating a population standard deviation, or variance, requires a simple random sample, and the population must be normally distributed, no matter the size. This one is a very strict requirement. We can't have any other shape of the underlying population. It has to be normally distributed. The confidence interval for the population variance is n minus 1 times the sample variance divided by chi-squared to the right is less than the population variance is less than n minus 1 times the sample variance divided by the chi-squared value to the left. The standard deviation, we could just take the square root of all three of these. So the square root of n minus 1 times the sample variance divided by the chi-squared to the right is less than the population standard deviation is less than the square root of n minus 1 times the sample variance divided by chi-squared to the left. You would round based for original data to one more decimal place than is used in the original data set, and from a summary statistic, you'd round to the same number of decimal places as is used with the sample standard deviation. So note the confidence interval for this is not plus or minus some error. We are not calculating an error for this confidence interval. So the procedure that we would need to follow, we would verify that the sample is a simple random sample and the population is normally distributed. Using n minus 1 degrees of freedom, we could find the critical value chi-squared to the right and chi-squared to the left, corresponding to the desired confidence level, and construct that interval, the confidence interval estimate for the population variance by taking n minus 1 times the sample variance divided by the chi-squared to the right and n minus 1 times the sample variance divided by chi-squared to the left. To get the confidence interval estimate of the population standard deviation, take the square root of each of these components, and you would round to one additional decimal point value if an original data set, or the same number of decimal places if using summary statistics as the sample variance or sample standard deviation, depending on what, well, sample variance for this actually. So for example, dataset 8 IQ and lead dataset lists IQ scores for subjects in 3 different lead exposure groups. The 22 full IQ scores for the group with the medium exposure to lead, group 2, have a standard deviation of 14.29263. Consider the sample to be a simple random sample and construct a 95% confidence interval estimate for the population standard deviation of the for which the sample was obtained. And based upon this, we have our histogram here. It's slightly skewed to the left, so, but is relatively normal though otherwise. So this might be a questionable thing to be built in to begin with, but it's relatively close to one, at least inside this general vicinity. But just to show that actual computation of it, we have a left limit and a right hand limit on here as well for this particular confidence interval. So for this particular one here, we would have 120.9 is less than the sample variance, population variance, which is less than 417.2. And if we take the square root of everything to find the confidence interval for the population standard deviation, this would be 11.0 less than sigma less than 20.4. The degree of freedom for this was 21. The actual calculation, since we would be using those chi-squared values from example 1, the actual calculation itself for these is 21 times 14.29263 squared divided by the right chi-squared value of 35.479, and for the 417.2, this was 21 times 14.29263 squared divided by the left chi-squared value of 10.283. And the overall interpretation for this, is that we have 95% confidence. We have 95% confidence that the limits of 11.0 and 20.4 contain the true value of the population standard deviation, so sigma. And to determine the sample size needed, we have this table here. To be 95% confident that S is within certain values, so 1%, 5%, 10%, 20%, 30%, 40%, 50%, of the value of sigma, the standard deviation, the sample size n, should be at least, and we have these values, so 19,205, 768, 192, 48, 21, 12, and 8, respectively. And to be 99% confident, for 1%, 5%, 10%, 20%, 30%, 40%, 50%, of the value of sigma, the sample size n should be at least 33,218, 1,336, 336, 85, 38, 22, and 14, respectively. And now, based on this table, we have an example. We want to estimate the standard deviation sigma of all IQ scores of people with exposure to lead. We want to be 99% confident that our estimate is within 5% of the true value of sigma. How large should the sample be? Assume the population is normally distributed. So we look at the table we just had on the last slide. So we want 99% confident, and the standard deviation needs to be within 5%. So that value, according to this table, is 1,336. So 1,336 would be that sample size from that table. Thank you.